chapter 3, is all about the stoichiometry. Stoichiometry stands for stoichio and metry, two words together. Metry is to measure, and then stoichio is anything related to more. It's a more measurement and more calculation. And as you can see in the first slide here, this is Avogadro's picture, and he carried a mole, an animal mole. However, the real mole is just a ratio between mass over molar mass. Or a mole, as you see, its number of Avogadro's number, 6.02 to 10 power 23 molecules. So in one mole, we have Avogadro's number of molecules, Avogadro's number of atoms, Avogadro's number of formula units, which is means ions. So we can look at this. So a mole defined is really the mass of whatever this is, the mass of an element that's really related. Related to the how many atoms in this element. This is equivalent to 12 grams of the carbon 12 isotope. But we'll be using more or less the ratio between mass over molar mass, which is equal to 1 mole. We'll be using this in each 1 mole fraction of atoms or molecules or ions for millions. So here it is. This one here gives us what I've said. This one all of the Avogadro's number of atoms, molecules, and 4 millions. This is, as you can see, the mole is a ratio between mass over molar mass. However, if you have an element, you don't have a molar mass element, so it will be atomic mass. So mass over molar mass for a compound, or mass over atomic mass for an element by itself, or one single atom. So, and here we have an example. If you look, this example here on this is it's asking for milligrams, and then in 12.05 moles of helium. Now we have to know the atomic mass of helium. What is the atomic? We're not quite very well, but I'm trying to. So atomic mass. We need the atomic mass of helium. Now, atomic mass of helium is given to you to be 4.003 kMe. This value is the same unit in gram per mole. So you multiply, so we need grams. So this is the given moles multiplied by atomic mass, not molar mass. We have one helium, it's one element. So multiplied by its atomic mass, the moles with the moles with the moles cancel out, and then we end up with grams. Now, you have to ask for the sig fix. Since we have this one here in the question, so our answer has to have 3 sig fix. 3 sig fix. We're trying to figure this one here. So 3 sig fix, and this is from the calculator, and this is the correct 3 sig fix. This is correct 3 sig fix. So now see the next is just to look at we looked at the one element helium. How about more compounds such as sodium chloride? So if we go back here, we have 20.25 moles of sodium chloride, this ionic compound. So we need to get the molar mass, M. M means not millimeter, no, molar. Okay, molar. So we need this molar mass of sodium chloride. It turns out to be sodium is 23. Sodium is 23 gram per mole. Chlorine is 35.5 gram per mole. They add themselves up to 58.5. Now, you have the number of moles given to you in 4 sig figs or sig figs, significant of 4, so 20.25 multiplied by 58. This is a month, but since we use the 58 gram per mole, this is 3 here, so the answer has to be in 3. So you have to go for scientific taken to get out of this 7 sig figs, significant 3 sig figs. Next, we'll see the unique thing about the stoichiometry is you can go from grams, which is very, very small amount, into number of atoms, molecules, or ions, formula units that it means. So in order to get into this, you should in order to get all of this, you will see you start with the gram, so start, and you will end up with the atoms, molecules, and formula units. What's unique about this value, the grams, are small. This is small number. Okay. And this is very, very large. So, therefore, if I have 100 gram of carbon, that's an atom, that's an element by itself. So I use atomic mass, not molar mass, no, atomic mass of carbon is 12 gram per mole. I put the gram underneath, so gram to gram will cancels out. So the gram to gram here cancels out. Now, this is, and then this step here, I have to divide. So this step here, I'm dividing by the molar mass. Divide by M and M, by MM. MM we said molar mass, MM we said molar mass. Now the next step is you will get number of moles here, correct? And that's what you get. Grams to one cancels out. You cancel themselves out here. So you end up moles. Now we multiply this, next step here. Multiply by Avogadro, multiply. By Avogadro, AB. So therefore you can expect the number will be very large, and that's what you can see. Number is very large. Now you have to watch here for those sig figs. So start with 4 sig figs. Right? Here is 5. And here is 4. So your significant here has to be 4, and this is correct. 4 sig figs. So now we started with small. Small. We'll end up with the large atoms or molecules or ions. Now, how about if I flip the equation? I'll start with the large atoms or molecules or like the ions. And then I need to get number of grams. So I'm expecting I start with a very large number. I'm expecting a small number. So I'll start taking that step. So let me, as I said, do this type of conversion, grab to atoms, molecules behind. or vice versa from atoms, molecules, ions into grams. This is covered in the final exam, ACS exam. So what I want to do for you to look into the whole thing and then maybe print out this and keep it handy to you for the quizzes or college quizzes and exams. So you need this here handy. So if I go from grams to atom molecules formula units, I have two steps. First, I divide by the molar mass to get rid of the grams. Then I multiply by Avogadro's number to get rid of the moles, right? So that I end up with the atoms molecules. Now, the opposite of this is this one here, which you start with the large number of atoms, molecules, or formula units, you end up with the grams. So we have to do the opposite. First, you divide by Avogadro's number. So this one here, the step one here, you have to divide by to get rid of the atoms, the unit atoms. So first you divide. So this one here divide. Here is multiply. So divide by Avogadro's number. Avogadro's number, and here multiply by the molar mass or atomic mass, multiplied by atomic mass. You have an element. Or by atomic mass. So half of atoms, as you can see from here, half of atom molecules and formula units, ions, you get number of grams. So as the example shows, we started with this amount, right? The first step by Avogadro's number to get rid of the number of atoms. Then you multiply by the molar mass so we can get rid of the here just to show you the whole step again. It's just to put emphasis how you can transfer this, the whole thing here. Will tell you how to transfer the grams into this will here from grams to atom molecules sorry, and formula units or ions. So this one here, we go here, then do the opposite. So from here, do the opposite. Yeah, going here, you get the opposite operation, and then we start with atoms, molecules, or ions. So let's look at an example here. Let's look at an example. So I pick it out. So what's the example here we can look into? Well, we can look into this example. We have an element this time, not a compound, an element, iron. Right? This iron here, as you can see, has this number of moles. And then we have to get the atoms, this iron. Well, this is direct, this number of moles of iron. You multiply this, you don't need any interference, you just the moles with the moles. So you have Avogadro's number atoms per mole iron. So you divide it, you multiply by Avogadro's number. You can always, whenever it's atoms, molecules, or ions, formula units are asked, you expect your value to be very, very low. And then you watch for the significant figure. So 3 significant figures given to you at the beginning, and the Avogadro's number is 4, 6 fixed. So end up 3 seconds. Now, here is totally different. Now, it does not give you a mole. If you give you a mole, easy. So you can use direct Avogadro, but you can skip you skip the steps of the atoms, molecules, and form by unit. So here it's giving you the graph in here. So, okay. And they want from you the atoms, and they want from you the atoms of iron. So what you will do here, as I say, I have to get through the first step of the graphs by dividing this one here by the atomic mass. The value, then the answer will be in what? We will not round in between, we just go on. So we divide by the atomic mass and then multiply by Avogadro's number. And that's what we happen. This is what started with. Divide by the molar mass, you get number of moles. Then the atoms is Avogadro's number, magic number here of iron per mole. So the mole cancels out with the mole here. And the gram here cancels. Okay, and the answer has to be 3 seconds. Okay, so if you look further, in this another example, here we are using molecules. This molecule is called H2O. H2O is used as a molecule, which is we have here 2 hydrogens and 1 oxygen. So this is 2 hydrogens and 1 oxygen. So you need convert number of grams, 0.2 grams into molecules. So from grams, small to large molecules. So we can expect the number to be very large. Now, if you look at the whole thing, you need, as I said, from grams into molecules or atoms or units. You have to first divide by atomic mass for a single element, or for divide by molar mass if you have a compound. The H2O is a compound made of 2 hydrogens and 1 oxygen. So first get the molar mass of H2O. We have 2 hydrogens, 1 oxygen. The atomic mass of hydrogen is 1, multiplied by 2 makes 2, and the oxygen atomic mass is 16. You will end up H2O is 18 random. So whatever is given to you, we divide it by 18. So therefore the grams cancels out in grams. Then next you have to multiply it by the Avogadro's number to get number of moles. And you have to solve for just what out for the specifics. Here is the moles, the molecules. So here we don't need them elements. Why? Because already the moles here and Avogadro is molecules by 1 mole. So the mole here with the mole cancels out with the mole here. With the mole here it cancels out. So just multiply your value with the Avogadro's number and then batch out and the sequence. Just it's 4 significant figures, and your answer has to be 4 sequence. And that's what we have here. That's correct. So now let's go and look at the comparison between 2 samples. We have different number of grams each sample, and then they have different molecular structures. So oxygen is O2, oxygen here, O2. If you look, hydrogen, I2. So those are molecules, not elements. It's they are molecules. O2, two atoms together of oxygen, it's O2. Oxygen molecule. So therefore, you need that. You got the molar mass. The molar mass of oxygen the molar mass of oxygen the atomic mass of oxygen is first the atom is 16 going up, multiplied by 2, makes 32. So 32 here, the number mole, this is the molar mass of oxygen. We take the 10 grams of oxygen, divided by the molar mass of oxygen, 32, 1 per mole, and then you multiply this one by Avogadro's number. So the mole cancels out, the grams and the grams. Grams and grams will cancels out as well. Okay, so I have this amount here. With iodine, the same thing, 50 grams of iodine. The atomic mass of iodine, you can look it up, right? So iodine is we need 2 of those. So the iodine 2 is 253.3 grams as per molar mass of iodine. So the grams with the grams. Would cancel out. And then you make what on the other to get number of moles. Now, do we need really we need to calculate? No, we don't. Look at the values here. This is a common one. This is Avogadro's number. Is considered to be common in both. So this number is fixed in both molecules. However, the whole molecule is divided, the whole amount divided by 32. Here is divided by 253.3. So that's a large. So if you divide any value but large number, so your results you can expect will be very small. So therefore, 32 of the oxygen is a small amount. So when we divide over 32, so you can expect the oxygen will have more molecules. So you see, oxygen will deliver for us more molecules than the iodine. Here we have an example. If you have given to us to our amount here, 18 grams of H2O. So how many oxygen atoms are present? How many hydrogen atoms? Remember, H2O we have H, 2 oxygen O equal to very important to know the ratios. Driving one oxygen. So we need to convert these grams first into using the molar mass of H2O, which is 18. We calculated 2 aggregates is 2 divided by 16 plus 16 of oxygen. 16 plus 2 is 18. So the molar mass of H2O is 18. And this is here. It's the molar mass of H2O. Now, I want to convert this one here to a number of moles. 18 grams divided by by 18 grams. Also, gram of cancels out. Now, you end up with one. So this is your answer. Now, in one mole of H2O, you have how many atoms of H2O? I believe 2. Have 2. So therefore, if we multiply this one by Avogadro's, you get this molecules, correct? One more, multiply Avogadro's, more cancels out, you get more. So this molecule here, you then for oxygen, one molecule for H2O has 1 atom. So this is very important, 1 atom. And here they have 2. So oxygen will remain the same thing because it's just we have Avogadro's number here. So you have 1 atom, 1 H2O, the number says the same, except Avogadro's number. However, the hydrogen, we have two atoms for one extra molecule. So therefore, the molecules will cancel the molecules, right? Have and that was multiplied by 2, you will get the number of hydrogen atoms. Now, this is a very interesting approach. This is just a ratio. This is not really that we are going from grams or atoms to grams, or molecules to grams, whatever. No, this is just a ratio. It's given to us, as I said, because of the different approaches for this supplementary shuttle. I would say you can put permission to print out those pages independently for you when you take the exam. But first, then you know what approach to use. There's just too many approaches. But it's not really this. But the main thing is, for the time being, is those approaches handed to you so you can control it. So let me see here what we have here. We have molecular. This is called molecular, not empirical, molecular. We'll come to this for a minute. So this one here called molecular formula. It has 3 carbon, right? So carbon is 3 and hydrogen is 8. And this molecular structure has this amount of atoms that's given to us. So let's set it up. I have 3 carbon, I have 8 hydrogens. So this one here we could translate it to, I have Y hydrogen. It has this amount of hydrogen. This is carbon, Y of carbon, and this. Okay, now let's look at this. 3 carbon to 8 hydrogen, and we have carbon here to number of hydrogen. This is given to you. Cross multiply. Work on cross multiply here. With this what? Solve for Y. Solve for Y. So Y we solve for. So Y here is came out to be, with consideration of the 3, we have 3 sig figs here. So we have 3 sig figs, your answer will be 3, and Y is this one. Okay, so you can even verify the value here. If this value here divided by this amount, we should be by this amount here, we should get the ratio 3:12. So let's take another example here. This example gives me this, and what is the total mass of the sample? Well, it's not really difficult. We know that we have this amount here, correct, of hydrogen. That's this one here. This one here of hydrogen is all of hydrogen. But we know hydrogen has 8 hydrogen. So you can get this amount of molecules in this C3H12. Now, this amount here, we divide this one by Avogadro, this molecules, Avogadro, to get number of moles. We need the total sample. The total mass means we need 1 grams. So we divide by Avogadro's number to get number of moles. So the answer. This number. Right now, we have to get the molar mass of this compound, 3 carbons and 8 hydrogens, which is 44 grams per mole. We multiply by the number of moles here. So here this number of moles with the molar mass. This we have 0.644 multiplied by the molar mass of C3H8, which is 44 grams per mole. So you end up this sample has total mass 27 grams. look at this now, we talked about the empirical formula, right? And shortly, but let's go and look at the whole thing. What is the molecular formula? What is the empirical formula? It turns out that the molecular formula give us the truth. So molecular formula here, molecular formula here. Okay, express the truth, right? So it has true ratio of the elements within the formula. So true ratios. True ratios. Uh, True ratios of the elements within the formula. The elements within the formula. So take this one here. Now say how about how about if we have empirical formula? Well, the empirical formula is the reduced form, simplest, smallest ratio. So the empirical formula, well, as they say here, it really express the relative smallest ratio. So within the atoms or elements within a compound, it has to be very small, smallest one ever. So if I have magnesium chloride, I say I have one magnesium atom to two chlorine atoms. This is when I look at the molecule as atomic level, at the atomic level. Now, magnesium chloride made of 1 mole, so 2 moles of calcium. This is when we consider the working out. Yeah, when we consider this one here as the moles, then it is molar. So if GCF2 is a molar, say magnesium is a mole and chlorine is 2 moles. That's a molar approach or molar level. If you say no, that's magnesium one atom and two atoms of chlorine, that's atomic approach or atomic level. So now we'll give you just an example. Glucose in our blood is C6H12, right? And O6. This is molecular, correct? This one here, this is molecular. If I reduce it by the common factor, which is 6, it will be 6, 1, H2, 1. So this is called the empirical formula, which is the smallest ratio of the elements within the compound. Right? So let's see how we approach calculation of empirical formula. It's not really difficult, but there's a lot of examples on how to approach it, how to do it. You'll be given a mass percentage of an element of the elements within the compound. First step. That's the most typical one. You'll be given the mass percentage. You assume that your sample is 100 grams. Transfer those grams into moles. That's what you're using there from mass of each element within the compound. Then you have number of moles, correct? Here you get number of moles. You divide by the smallest number of moles, so that the whole ratio is without any fraction. And then you can assign your y, I, smallest number. Okay, and then you assign your empirical. Now, if you look at this, An example. What is the percent composition of ammonia? Well, if you look at this, turns out to be 200 of ammonia, correct? The first thing of approaching those type of questions here, you need the molar mass of the whole ammonia. Percentage composition means you divide each element mass or molar mass or atomic mass or element of atomic to the total, one, to the total molecular. So we take atomic mass of each element we talked about divided by the molar mass of the sum of all those atomic masses, and then you multiply by 100 to get that amount. And you have to always consider the number of atoms within this compound. Ammonia, for example, has how many? Has 3 hydrogen to 1 nitrogen. So we have to add them. So when I go there, I need to get the molar mass of ammonia on the compound made of 1 nitrogen, 3 hydrogens, atomic mass of nitrogen is 14 bonds or 1 mole. By 1 is related to 1 is related to. So then plus 3 multiplied by what? Oh, by 3 because we have 3 hydrogens here. We have 3 hydrogens, and the atomic mass of hydrogen is 1. So you end up having a total molecular mass for the whole NH3 on nitrogen 3 hydrogen 70. Well, it's all gone. Now, atomic mass of nitrogen is 14. You divide them by the total. That's atomic mass. Divide by the total molar mass. Multiply by 100. And then the 3 here, multiplied by the total 17. Multiply by 100. You add those up. What will be? You have to come up with so without calculate this one has to come to 100%. Okay, so here is sodium thiosulfate. We want to get the percentage of composition. Well, we need the molar mass first of the whole thing. We need the molar mass of this compound. 2 sodium, correct? 2 sulfurs, sulfur atoms, and 3 oxygen. So this one here, atomic mass of sodium is 2 atoms sodium multiplied by atomic mass 23. This is very good, 23. And 23. Sulfur is 32. Sulfur has 2 again. So 2 multiplied by 32. And oxygen is 3 by 16. So we add all this sum here, as we did here, 2 for sodium, 2 multiplied by atomic mass of sodium, 23. 2 multiplied by sulfur, 32, 20 mass. 3 multiplied by 16. With the value of 158 grams. This is the whole sum. Now, I have to take each element by itself and considering its amount. So we have sodium, we have 2 atoms of sodium. Atomic mass of sodium is 23. Divide the whole thing by the total sum of the molar, sum of all the atomic masses. So this is a molar mass. And we multiply it by 100. Sulfur is 2 atoms. And 32 is the atomic mass divided by the whole thing, which also so 3, level 16, then more, 158. And then if you add all those up, you will end up having 700%. So now, so look here. And let me look here. Now the copper sulfate 500. They want to see what's the percentage of H2O. Well, the idea is very simple. You have to get the molar mass. The molar mass of this compound first, copper sulfate, and then the molar mass 5. This is 5 H2O. Okay, so the molar mass will be 7. So copper sulfate by itself and 5 equals H2O by itself. Copper sulfate is made of 1 atom of copper, 1 atom of sulfur, 4 atoms of oxygen. So therefore, look at this. This is copper sulfate. Copper has atomic mass of this 63.5. The sulfur is 32, and the one of it is 4,000. That's one of it. And then we have 4 of oxygen, so we have 16. And then you add them up, then this is the molar mass. 5 H2O, 5 H2O, we have 5 here. 2 hydrogens and 1 oxygen H2O. Two multiplied by 1. I want to have more. 10 plus of hydrogen is 1. You have 2 of them here. And oxygen is but you have 2 of hydrogen, you have 1 oxygen, which is 16. And then you add them up, it's 18 for H2O, you multiply by 5, goes 17. And everything is, you have to consider all the atoms, so it's 5. So the 5 molecules, they have this. Now you have to add those two together to get the total of the whole thing. When you get the total of the whole thing, guess what? You divide them, the 90, you divide this by the total. 5 and the total. And the total. So that's what you have. 90 divided by the total. It's you of 36. But you have to consider the suffix. So let's look further. And here, in this, we calculate mass percentage composition from masses of the element. Well, we have the sample, C group. The sample, the total sample is this. So that's what we divide everything on. So we have to get first sample. So we have what? We have this amount of carbon, this amount of oxygen, and this amount of fluorine, right? Well, we divide the amount is carbon by the total, right? By we divide carbon 12.0 by the total. We come to this. And 17.2. You divide the oxygen 4 grams by its total, the sample, fluorine 17.8 by the total of the sample, and you get the percentage. And if you add, those has to be equal to 100%. So that's equal to 100%. Okay, so let's take another example here. Another example, we have chloroform as percent composition of this percent of carbon, this hydrogen, this chlorine. Determine its empirical term. Well, you know chloroform is CHCl3. So CHCl3. So let's calculate this. Let's look at this example here. So we have, it's given to us, that's question here. So give us here the percentage. So the percentage is given to us here. So we have to look into numbers here. So carbon is 10.06. That's the number example. Hydrogen is 0.85. And fluorine is 89. So this is the percentage. So what to do? Because this is 100%, it has to add itself to 100%. So we assume our sample to be 100 grams. So this is very important. First of all, you will say, okay, the sample is 100 grams. So sample is 100. So those are the percentage into grams. Okay? And if you add them up, this has to be 100 grams. Okay? So now you can use atomic masses for each element. Carbon is 12 atomic mass per mole. Hydrogen is 1 gram per mole, and fluorine is 5.5 gram. You divide, take those grams, you divide them by their atomic masses to get number. So it is we divided by the atomic masses to get number. This is the number of moles here. This is okay. Now look at the whole thing. You divide by the smallest. The smallest is this one here. Divide, this one will be 1, this one will be this one will be 3. So it will be COH. CL. So this is the empirical formula, so we can even verify it. So let's go further and look at this empirical formula. This is 113, and this is came out to be, see what we say. This is the empirical formula of chloroform. We have to note here, this is the same thing with the molecular form. Sometimes the empirical formula and the like H2O, it is 2 to 1. This is molecular formula. But the same thing, and empirical formula is the same. You cannot reduce that formula. So and the same thing with the Coulomb formula. Coulomb formula is cannot reduce W1, 1, 3, cannot be reduced further. So empirical formula is equal to the molecular, actual molecular formula. And by the way, the chloroform is used to, to put people asleep. So that because ether was used now, ether's are very highly flammable, and it's not really easy to handle high flammability of ether. So we use chloroform and some other chloroform by far is safer to use than ether. So let's look at the example here. We have this example here. We have example. The compound, 33.3 grams of the compound has. So the total, what is this? This compound has phosphorus, fluorine, this amount. So E first is the atomic mass of phosphorus, atomic mass of fluorine. Right? Then we take the grams of the phosphorus, right? That's the grams of phosphorus divided by the total. First of all, we have to get that gram to get that. Remember, all the idea to get number of moles. So 0.7 grams of phosphorus divided by atomic mass of phosphorus to get number of moles. This number of moles. Fluorine is 2.50 divided by 0.5. Let's do this one. Correct? So if you look at the whole thing, this number of moles will be divided by the smallest one, 0.02 and 0.07. So first process is 0.02 by smallest. So this one will be 1. And this one here will be divided to this one. As you can see, one will be 1, the other one will be 3. So what is 1? Okay, so we divide by the smallest number. And the other will give you 3. So the numerical formula is CL3. So this is the numerical formula as well as the empirical formula as well as molecular formula. So they have the same. So let's another example is very important to know the ratio between the molecular formula and empirical formula. We said sometimes they are equal, sometimes they are not equal, but they are related to each other. So see gram per mole, or A and U atomic mass unit. So if you look at this, this is the molar formula. This is empirical molar mass. This is 2 molar mass, correct? So if you look at this, the gram cancels out. Those will cancel out. So then it came out to something called N, it's a constant, called N formula units. By the molar mass, the actual 2 divided by the empirical one, the reduced simple ratio of the elements. So molar mass by the empirical mass is equal to value for N, which is N formula units per molecule. So you can multiply, you get to you can calculate this from the molecular mass or molar mass by multiplying M by M. Let's see. Here we have the source of the molar mass. So the molar mass is N formula per molecule multiplied by the formula. So let's look at the next one. Let's look at the example. The hexane, by the way, is not, this is a typo. It's hexane typo, but we'll do it. So don't worry about this one here. This is not hexane part. Hexane is C6, the formula, the molecular formula, C6H14. So what? C divided by 2, C3. Oh, that's correct. That's the empirical formula. Yeah, that's correct. So that's it. So and it has the molecular weight, the molar mass. That's correct. Molar mass of the whole is this. And give me the molecular empirical formula, or give me the molar mass, the whole thing. What is the molecular formula in the structure of 6? I gave you C6H14, correct? That's without calculation, but we have to calculate to verify that's really true, right? So let's do it. We have molar mass, the true one, empirical formula mass equal N, correct? Now we get this one here. This one here we given to us is 46, right? This one here is the empirical formula C3, C3H7. 3 carbons plus 7 hydrogen is 1. Hydrogen is 1. And this is 12. So 7 multiplied by 1, as you see here. So and then 3 multiplied by 12 for carbon, and 7 multiplied by 43. So 86 divided by 43, that's the formula units. Mass. Divided by the so you can see here, that will give you 1, give you 2, correct? Ratio is 2. So this one here is ratio is 2 to 1. So cross multiply, molar mass will be 2 multiplied and their component, right? So 2 C will be C3 mucus, by 2 will be C6 H14, and that's what we have here. So let's look at this. Another example. So this is under here as well. Then now compound dioxide contains only carbon. Make it smaller. We have carbon, hydrogen, oxygen. So we have 3. When dioxide is burned, it's the total mass. It's the total mass. It's the compound of dioxide. Burned, we get 1.9 grams of carbon. Right? The mass of carbon, which is 12. Carbon dioxide. This is carbon dioxide, not carbon. So this one here is let's see, carbon dioxide has this amount of 1.9 grams of carbon dioxide and 178 grams of H2O. Correct? And it was determined that this amount, this here, amount of grams per mole. This is the molar mass of dioxide. This is because it was determined by experiment this amount of grams per mole. So this is the molar. So what is the molecular formula? The structure of dioxide. Molecular structure of dioxide. Now, if you look at this, you first have this 1.91 carbon dioxide. Carbon dioxide is CO2. H2O is H2O. And it has oxygen as well. So you have 3 of this. So you have what? You have 3 of those. Okay? So you have 3 of those, and then out of those, if you look, out of CO2, the molar mass of this, which is 44. Okay? I have 1 mole of carbon, 1 mole of CO2. I have 1 mole of carbon in 1 mole of the molecule CO2. I have atomic mass of carbon 12. I have 1 mole of carbon that has 12 grams. So I'm transferring the whole thing into grams. Okay, so for hydrogen, same thing. I have H2O here. The molar mass for H2 is 18. I have 2 hydrogens. H2O. So then you have, look at that. You have 1 gram of atomic mass of the. This is those here are atomic mass of diamond. So the more cancels out, we have 2 moles of hydrogen to 1 mole of H2O. So now you ask us how we get the absolute. Well, if you subtract those here together, you get the absolute. Right? So absolute will be subtract those two. Subtract them to get to the absolute. So then we have number of grams of carbon, which is this. Right? We need to transfer those into moles. Divided it by its by its abundance. Number. So the thing that we like this. We divide the hydrogen by its number of grams. After you divide it by the here's at the time, no, this should be gram, but no, this is a 16 one. So it's supposed to 16. Atomic mass of but atomic mass was a 16. No, you get this up to 16. So you have this ratio. What is the smallest ratio? Burnt of for 3 is the carbon, smallest one. The nitrogen, smallest one, or burnt of 2. Turns out to be actually the smallest one. Right? Over here. So now we get all those ratios here. We get all those ratios here. This to this to this. Right, but the smallest one. So the smallest one is 0.02, that's the smallest one. So answer will be 1. Then hydrogen almost 2. Hydrogen is more than 2. Right, so it turns out to be this is the empirical formula. So we all can do that. So the molecular weight of the dioxin is less than 3 grams per mole. And that's what we say we have to circle this one here. So when you go back and look, so it is. So you can tell me this the whole compound is given to you is here. So this one is the whole, this is the mass. Put together the source over here. So calculating the number of moles, the whole saying is equal. So now we have the formula is 2 to 4 to 1. The non-oxygen, 2 carbon, 4 hydrogen. So you can see that's the empirical formula. You be careful. So this is you divide all by small amount. Small as 1 is 1.2. So actually it's small. Then you can see here now to 1 oxygen or 2. So without that one, this is empirical. Empirical formula came up to be 4. So PTE divided with the elements. This is American. It's a weight of it. So that's 2. So you multiply the molecular structure will be multiply those by 2. So it will be C2 H4 1 and C4 H4 H8 14. That's the better problem of dioxide. This is another class example we have to go through and then stop and then we can come back again and then prepare for you the other. Let's look at this class example from paper. The compound ethylene glycol and ethylene glycol by the way can be uses center and antifreeze. So that's the idea. So it's very important. Like it is fast. And to feel so extra just before. And there are data of the class will be destroyed. So we have this compound ethylene glycol to recover this. Use this antifreeze, as I say, it contains 37% of carbon and 17 of hydrogen, and the rest is oxygen. Molecular formula, the whole molecular formula is this spirit of. What is the molecular formula structure of the glycol? Well, I remember I remember just to see if we are correct. So this is H, this is H. The ethylene glycol is dialkyl. So OH here and OH is here. So we have carbon is two carbons. How many hydrogens we have? 1, 2, 3, 4, 5, 6, 6. How many oxygen we have? 2. Also, this is the molecular formula of the ethylene glycol. Now, is this correct? Let's examine. It will be very interesting to see. So we assume the sample is 100%. That's the first thing. So we have percentage. So then we have carbon is 38.7 grams, correct? Then we have hydrogen is 9.75 grams. And the oxygen will be the rest. 100 minus, oxygen is 100 minus plus grams, correct? Oxygen is this. Now, calculate, first of all, assume 100 grams of the sample, transfer the percentage into grams, and the next to get the moles. So very important to get the number of moles. So number of moles is carbon. This is the amount of carbon, the grams of carbon from percentage to grams divided by its atomic mass. We give you this number of moles. Hydrogen, this is the number of the grams, the percentage divided by its atomic mass. We give this number of moles. Oxygen is whatever is left over from subtraction. This is this oxygen now divided again. This is all kilograms. So this is 16. So I get this one. So the atomic, you look, the molar mass is given to you 62.06, correct? So, and if you look at this, let me just go and make the smaller. If you look at this now, very interesting. Which is the smallest one? Well, it looks like the empirical formula from here. Carbon divided by the smallest one, which is this number. Correct? So carbon is 1. Hydrogen, we see how much hydrogen is. Hydrogen is, and oxygen is 1, correct? Now, hydrogen is 9.67. To me, hydrogen is 3, 6, 9, 3. I think it's 3. I can verify that. I can prove that. We are calculating 9. Yeah, it's it's 3. So now you get out of this the molar mass. 3669. Yeah. So the molar mass of this is 1 carbon is the molar mass is 12 plus hydrogen is 1 is 3 plus 16. Right? So the molar mass is 15 and 16 is 31, correct? So this one here is that's the empirical formula, that's the molar mass of the empirical formula. 19, 15, and it's 31. 31. It's not 19, it's 31. Number more. Right? However, here Actually, my second gap is 62 volts per second gram, so it has to be. So 32, so take 62 divided by 29. How much is it? 2. Right? So this is 2. So the molecular formula would be 2 divided by C1 H3 or this is 2H6 would be sorry. H6. This is 2. This is 2. Oh, super, super, super. This is, it has to be C3 H1. So when you multiply by 2 will be carbon 2, hydrogen is 6, and oxygen is 2. This is the same thing is here. Same thing is here. Look at this. This value here, this, look. We got by the calculation, and I just, I told you I know the formula of it. Give me the formula, and that's what it's up to. So this is excellent. Yeah. And we can look at this. This is 2. Multiply this one more by 2, it is 2.602. So if you look at this, it's same formula we did. So this is C2O6. Let me just remind you before we quit. So this is 2 carbons. This is 2 hydrogens. We were 2 hydrogens. It's here. This is. Thank you very much. I'll stop now the recording and we'll take them this time. Thank you very much. Thank you.